Hello. I hope you are having fun with our cone buddies. Now that you have understood their different paths and also their surface area. But to be best friends, you need to know them better. So, what's the one thing that is yet to be known about cones? Correct, their volume. So, let's take today's video to understand how do we calculate the volume of cones. So, ready to strengthen your friendship with them? Let's begin. First things first, what type of a cone are we dealing with? You remember that there are different types, right? There are those which are right circular and then there are those which are not right circular. However, in this chapter, we are only discussing cones which are right circular. Remember why they are called so? Well, the name has the answer. Right circular cone. Right because the axis, which is the line joining the apex and the center of the base, is at a right angle to the base. And circular because the base is a circular disc. So, now that we know which shape we are finding the volume of, the next logical question is, how do we do it? How do we find the volume of a right circular cone? Well, the actual method of finding the volume of a cone is not very easy. It is something that requires calculus, a whole different branch of mathematics that you may be exploring in your higher classes. But what about now? We do not have any knowledge of calculus. So does it mean we won't be able to find the volume of a cone? Not if we are willing to get our sleeves a little drenched as we perform an interesting experiment. Now, before we rush right into the experiment, we must understand that this experiment will actually help us find the capacity of the right circular cone. But volume and capacity are used interchangeably, right? The only difference is volume is the amount of 3D space a solid occupies, and capacity is the maximum volume of substance a hollow container can hold. They are more or less the same, which is why we use the same formula to determine volume and capacity, as we have already seen in our previous videos. So now, coming to the experiment, we would need a right circular hollow cone, a right circular hollow cylinder and some water. Now, this hollow cylinder may have any radius and any height, provided that the hollow cone has the same radius and the same height. So let's take the radius to be r and the height to be h. Then basically both these shapes have radius r and height h. Now let's pour water into the hollow cone right up to the brim and then upturn it over the hollow cylinder such that the water pours completely into the cylinder. We see that only a part of the cylinder is filled and there's quite some parts still left. Now, what do you think is the volume of water in this cylinder? Whatever it is the same as the capacity of the hollow cone. Make sense? Great. Now, let's repeat the process of filling water right up to the brim of the cone and then upturning over the cylinder, making sure that not even a single drop of water pours outside. We see that the cylinder is filled further, but then some part of it is still left to be filled. So, what's the volume of water in this cylinder now? Twice the capacity of this cone, right? You are getting the picture. If we repeat the same steps one more time, ensuring that there's no wastage of water at all, we will see that this time the hollow cylinder fills completely right up to the brim. So, what do we infer from this experiment? We infer that the capacity of this hollow cylinder is the same as thrice the capacity of this hollow cone. Or in other words, the capacity of the right circular hollow cone is 1/3 the capacity of the right circular hollow cylinder. So we already know how to find the volume or the capacity of a right circular cylinder, right? The base is r and the height is h. So the capacity of this right circular cylinder is just pi r squared h. Then the capacity or the volume of this right circular cone is 1/3 into pi r squared h, which is nothing but 1 by 3 pi r squared h. So basically, the volume of a right circular cone with radius r and height h is calculated using 1 by 3 pi r squared h. That's a pretty interesting way of finding the volume of a right circular cone, isn't it? Even though this isn't the actual derivation, until we actually learn calculus, this serves as a good stopgap. What's a stopgap? A new word for you to explore. For now, let's use the hot information that we have just accumulated and solve a problem. Say you have a piece of canvas that spreads across 553 square meters. Now, you want to make a conical tent out of it with a base radius of 7 meters. Assuming that all the stitching margins and the wastage incurred while cutting amounts to approximately 3 square meters, we need to find the volume of the tent that can be made with it. Pretty interesting a question, isn't it? Now, to solve such a question, I taught you an approach, remember? What quantity does the question want you to find? What's the formula to find that quantity? And then, what's required to be known for that formula? So here, what quantity does the question want you to find? The volume of a cone, essentially. And what's the formula? We just studied that we can find the volume of a cone using 1 by 3 pi r squared h, where r is the radius and h is the height. So, what's required for the formula? Just the radius and the height. Now, the radius r is already given as 7 meters. All we need now is the value of h. But how do we find that? Play around with the information we already have in attempt to find the value of h. Now, the question tells us that you have a canvas that spreads 553 square meters, which basically means that the area of the canvas is 553 square meters. But how do we know that the question is talking about area? Well, the unit gives us a hint. Square units measure area. Now, the stitching margins and wastage amount to 3 square meters, which means that while constructing the tent, 3 square meters of canvas was either used in stitching or was wasted. So basically, the amount or the area of the canvas actually used to make the conical tent is 553 square meters minus 3 square meters, which is basically 550 square meters. Now, if you just think about it, the floor of the conical tent will not be covered in canvas, right? So basically, the complete canvas will be used only to form the curved surface of the conical tent. Or in other words, the curved surface area of the conical tent is 550 square meters. So, taking radius as r and slant height as l, we have pi rl is equal to 550. Now, taking the value of pi as 22 by 7 and r as 7 and then substituting in this equation, we get 22 by 7 into 7 into L is equal to 550. Now, 7 obviously gets divided and we are left with 22L is equal to 550. Simplifying further, we get L is equal to 550 by 22, which is nothing but 25 meters. So, L is equal to 25 meters and R is equal to 7 meters. Now, if you remember, we have discussed earlier that L, R and H are related such that L squared is equal to R squared plus H squared, since they are just the sides of a right angled triangle. So basically, 25 squared is equal to 7 squared plus H squared, or H squared is equal to 625 minus 49, which just simplifies to 576. So basically, H is equal to root over 576, which just simplifies to 24 meters. So, now that we have both R and H, applying them in the formula 1 by 3 pi R squared H, we have the volume of the conical tent is equal to 1 by 3 into 22 by 7 into 7 into 7 into 24. Now, the common factors get divided and we are left with 22 into 7 into 8, which just simplifies to 1232 cubic meters. So basically, the volume of the tent that can be made with the given canvas, excluding the extra 3 square meters, is 1232 cubic meters. We finally got the answer. Actually, this question wasn't difficult at all, but we invested more time in it just so you get the approach right. The right approach is very important while solving problems. Without the right approach, you may be able to solve the problems. But with the right approach, you will be able to solve them much faster. And to get the approach right each time, practicing problems is a must. So let's use the coming video to do just that. You will be needing your basics there. So let's quickly summarize and catch me in the next one. So in this video, we got closer to our cone buddies by learning how to find their volume. We saw that a right circular cone is one where the axis is at a right angle to the base and the base is a circular disc. Using a right circular hollow cylinder and a right circular hollow cone with the same radius and the same height as the cylinder, we performed an experiment and inferred that the volume of the right circular cone is 1/3 of the volume of the right circular cylinder. The volume of a right circular cone is calculated using 1/3 pi r squared h, where r is the radius of the cone and h is its height.